In this video, we will solve the second problem of IIT JAM 2021 mathematics paper. First, we will see a method that will quickly give us the correct answer. This method will also help you in the exam. I will also show you the mathematics behind the correct option, which will immensely help you develop your knowledge application skill. Let's get started. Now this is an MCQ with 4 options, only one is correct option. First, what you do is apply what I call the quick method. In this method, you eliminate the wrong options, and if you're lucky, you will be left with the correct option. Now, in this problem, we have a differential equation. Here is a rule of thumb for differential equation. When dealing with ODE, what you should do is you try to guess the solution for the ODE. This helps, this works most of the time. So the keyword to remember here is whenever ODE, you do trial and error. Now in this problem, see, this is a homogeneous differential equation. The zero function satisfies the differential equation trivially, right? Here's the differential equation, and it's satisfied by the zero function, and this function also satisfies the given condition y equal to yb equal to 0. Now luckily, this example also helps you eliminate the options B, C, D, because it is neither positive nor negative, and it doesn't even change sign. So these options are eliminated. So what we're left with is option A. Now if you're wondering why option A should be the correct answer and how we can prove it, then hang on, we are going to discuss just that. Now remember that in this problem, y is a twice differentiable function satisfying this differential equation and some extra condition. Before getting into the solution, here's something important about twice differentiable functions that we will need. First, we will discuss two necessary conditions for maxima and minima of a twice differentiable function. For a twice differentiable function. Now, if you're wondering why these conditions, hang on, it will be clear in a moment. So remember, we are trying to find the necessary conditions for maxima minima. Now consider y, which is a twice differentiable function on interval AB. Its graph is going to look something like this. So here you have A, here you have B. Suppose this is the graph of the function. Now this point xi is a local maxima, right? And this point eta is a local minima. Now here's the necessary condition. First one is something you must already be familiar with. It is called the first order necessary condition, which says that every local minima, local maxima must be a critical point. What does that mean? It means that the derivative of the function, the first order derivative, must be 0 at these points. Now the second one is a less obvious and important one. It says that the double derivative of the function is less than or equal to 0 at all maxima, and the double derivative is greater than or equal to 0 at all minima. Now if you're wondering why this is true, here's a quick proof of this fact. It will be interesting to see graphically, that I leave it to you for visualization. Now because z is a local maxima, you can have this inequality. Yz is greater than or equal to yz plus t. Now do the Taylor expansion of yz plus t at z, and the Taylor expansion up to double derivative is given by this t square double derivative z plus a remainder term, which is little o of t square right here. Now remember, y prime z is 0, right, because of the first condition. So here we have y prime z equal to 0, and yz cancels from both the sides of this inequality. So what we get from here is that y double prime z, the double derivative of y at z, is less than or equal to little o t square divided by t square, and this quantity by definition goes to 0 as t tends to 0, And by taking t tending to 0, we get this inequality y double prime z is less than or equal to 0. Now by similar method, you also get the inequality for the other case. Very well. Now let's get into the mathematics of the right answer. Now consider y to be a solution for the given problem that we had and focus on the interval a b. Now consider case 1. Let's assume that y takes positive values in the interval. Now its graph is going to look something like this. Here you have a, here you have b. It takes 0 on ab and the graph will be something like this because it takes positive value, and we know that every continuous function closed and bounded interval takes local maxima and minima. It's going to have maxima, call it z, somewhere in the interior of AB. So y has a maxima, say xi, in the interior AB, and by the first order necessary condition, which is also called first order derivative test, we have y prime z equal to 0. Now since y is assumed to be the solution of the differential equation, it must also satisfy the differential equation at z, which is given by this, and y prime z is 0, so this implies y double prime z is yz, which is greater than 0. Now z being the local maxima, we know from the second necessary condition we discussed earlier that y double prime z must be less than or equal to 0. So we get a contradiction here, right? So what does that mean? It means that y cannot take positive value on AB. And yeah, the case 1 is not possible. So what we do now next is we consider another case. Case 2. Suppose y takes negative values on AB. Now you can use a similar argument to prove that this case also doesn't exist. I leave it as an exercise for you. So what is the conclusion here? The conclusion is that y can neither take positive value nor negative value on interval AB. So the only option that's left is that y is a 0 function, and hence this completes the solution.